Well, thank you, everyone. Thank you for joining. So yeah, I will start. I will explain today how my project on using deep learning to characterize explosive volcanism on Mercury. So let's get started. So for those of you who are not familiar with Mercury, we see here at the center of the slide an image of the planet as seen by the MESSENGER mission. So at the left, we have an image, a monochrome image from the MD's camera. And then at the right, we have a false color image that I'm going to be showing throughout the talk. This false color image is obtained by using different PCA components from the MD's camera, which is based on only 11 spectral channels. And this image is very useful, has been very useful to highlight several spectral properties of the planet. In Mercury, we find this phenomena of explosive volcanism, and this is characterized by explosive eruption that occur through a central vent. And here at the right bottom of the image, we can see an example of the vent, which is an irregular and rimless pit. And then surrounding this vent, we have the products of the eruption, which are pyroclastic deposits, so deposits of these pyroclasts. These are characterized by having high reflectance, red spectral slope, and by being diffused. And we can see an example of one of these deposits at the top of the figure. These features have been found in more than 180 locations through the surface, and they are often located inside impact craters. And although they have been previously studied, there are still many unknowns. And just to show some of these unknowns and the challenges to study them, I have this slide with, so one of the main unknowns is to know the precise age of these features, and also to know the source and depth of the activity. And another important unknown, which is what we will be focusing on here today, is the spatial extent. So how far do these deposits extend? And the reasons why it's so hard to characterize these features is because they show very diverse forms. And just to show here some examples, we see that the eruptions can occur through single vents or through compound vents. Then, as we see on the center of the slide, they can be isolated, or they can be overlapping deposits where we have eruptions very close together that create deposits that overlap. And then, although we said that the spectral properties are characterized by having a high reflectance and red spectral slope, we see on the right that actually this can also be seen in very different forms. And we see here two very extreme examples with the Nater facula that's very bright and the Hemingway deposit that's very dark. So all in all, we have very, very diverse deposits, and we have a large amount of data. We have some data from this MD's camera that has a good spatial resolution, but only 11 channels. And then we have a data from a spectrometer that has a good spectral resolution, but a bad spatial resolution. So the goal of this work is to put this together and to understand these deposits in preparation for the Bepicolombo mission, which will have instruments with both good spectral and spatial resolution. So why do we want to study the extent of the deposits themselves? Well, the reason is that this extent gives us actually a lot of information on the eruption itself. So it has implications on, for example, the amount of volatile that was needed to emplace these deposits, also on the source of the eruption, the geometry of the eruption, and so on. So it's important to actually characterize their extent. The way this has been done in the past is by looking at these false color images. So we have here the Nater facula on the left with the monochrome filter image, and in the right, the false color image. And we see that the deposit is highlighted in this false color image with these yellow colors. So previous studies, what they have done is to take this image and then use it to constrain the extent. And for example, this is how it would look with the work from Kerber et al. 2011. The problem with this, or the limitation of this approach, is that actually the extent of the deposits, the apparent extent of the deposits, is different depending on the wavelength that we are looking at. And there are even more complicated interactions within the spectral domain. So for example, here we're looking at data from the masks spectrometer that has been interpolated to create these maps at different spectral wavelengths. And we see that the apparent extent of the deposit when we look at the normalized reflectance, it's different if we look in the UV or in the visible or in the near infrared. So this has been already assessed by previous authors that have revealed that with masks data, we find actually a larger extent of the deposit than with MDIS images. And this has been done by assessing the range of reflectance with the distance from the vent, and then looking at where this slope break happens and therefore defining the radius. However, the limitation of this approach is that it works when we have deposits that are perfectly circular and symmetric, but when we have more complicated deposits that are irregular and asymmetric, it doesn't provide a clear extent. And this is actually the case for many deposits that are not circular because they are overlapping or created in oblique eruptions or with compound vents or with interactions with the topography. And we see here some examples of irregular deposits. So the objective is that we will use this deep learning methodology that allows us to look into the data both in the spectral domain and the spatial domain in order to avoid this limitation. And okay, now I will get into the methodology itself. And again, we will use data from the masks spectrometer, which is working between 300 and 1,450 nanometers. And I will first briefly describe the general structure of the architecture and the general idea. So the objective is to inspect the data in the spectral and spatial domain simultaneously and to be able to extract the deposit extent from them, and also to get significant features that are characterizing the data. So in order to do so, first we select the footprints that are interesting for us in the region of the pyroclastic deposits in this case. And from that, we process a hyperspectral image because we are starting with individual point measurements and we want to get a full hyperspectral image. And then we use the neural network that I will get into more detail in a minute. But this neural network, what it will do in essence is to reduce the dimensionality of each pixel by compressing information not only from its spectral domain, so the spectra of each pixel, but also from the surroundings, so that it will be able to extract both spatial and spectral features. Once we have the network trained and we have this dimensionality reduction, we do two things. We first interpret these features, and then we create cluster maps that allow us to get the extent of the deposit. So this is the exact architecture that we are using. It's a three-dimensional convolutional autoencoder. For those of you who are not familiar with autoencoders, the basic principle is that you start with an input. It can be a spectra, an image, or in this case, it's a hyperspectral image. And then you have a set of layers with different filters that are extracting features, reducing the dimensionality until you get to this latent representation. And then again, you go up, you increase the dimensionality until you reconstruct your input. So once the network is fully trained, the latent space is actually a representation of your input. And in this case, we are using a three-dimensional structure because this way the operations are able to capture the interactions between the spatial and spectral domains. And I will not go into more detail with the architecture, but feel free to ask any questions later. So just to show some parameters of this architecture, we use as input patches of the hyperspectral image. So we don't provide the entire image of a deposit, but we provide patches around a single pixel. And as an output, we get for each pixel the number of latent dimensions that we select. There are some parameters, and yeah, once again, it is very important that it's extracting for each pixel information from both its spectral domain and also the surroundings. So for this case, we study a set of parameters and how they affect the results, such as the patch size, number of clusters, and so on. And again, I will not discuss this here, but it has important implications in the results. So feel free to ask questions if you are interested. And then there are other parameters that we keep fixed as it was proposed in the original architecture. So the first result that we look into are these extracted features. The majority of the feature maps, they look very close to some of the wavelength maps. So they look very close to, for example, the monochrome image or images at different wavelengths. However, there are some features that stand out. And here I will just highlight 2 examples of features that are showing information that is not directly correlated only to the spectra itself. So on the top, we have false color images for 5 different deposits. And then we have the 2 different dimensions that we want to highlight. In the center, we have a latent dimension that's actually showing this yellow rim of high value of the latent dimension at the edge of the deposit. So it looks like it's highlighting the edge of the deposit. What we think that is happening here is that the neural network is extracting the point where the gradient of certain wavelengths goes to 0 or goes closer to 0, and this corresponds to the limit of the deposit. However, this is not easy to correlate with the raw data, since it's already also having information from the entire spectral domain. But it's very interesting to see that it's actually extracting this kind of information. And then another interesting dimension, we show it at the bottom. It's highlighting in yellow the point where we have the pyroclastic deposit, but it's very interesting because in the background we see it as the latent dimension goes to 0. And while in the false color map we see a wide range of values for the background terrain, or it can be very, very diverse. In this case, the background is pretty homogeneous and pretty close to 0. So it will also be very interesting to understand what it's how this dimension is behaving. Now that we know that this kind of information is being extracted, we use the latent dimensions to create cluster maps. And here I show some examples of the cluster maps compared to the false color image. So basically, when we have a deposit that the properties of the deposit are evolving and they are getting closer to the background terrain, so the cluster maps show these kind of concentric ring structures as they go farther away from the central bend. In an ideal deposit, this concentric structure will end up in a homogeneous cluster, and therefore we'll have kind of this concentric structure seeming to be put on top of a homogeneous cluster. However, this is not always the case, and we don't see these perfect structures anywhere. But still, this allows us to define an inner cluster and an outer cluster that's defining the background terrain. And from this, we can extract the boundary of the deposit. So here we show an example of the boundary compared to the deposit, which is this kind of cloud structure found here. And we can compare it to the radius or the deposit size by previous authors. And we see that in this case, it's pretty close. And it's also pretty close to the circular shape. We do this for a total of 55 deposits. 35 of them are isolated, and 20 are groups formed by multiple vents. So in total, we cover 110 vents. And now I will just show some examples quickly of how these the results are improving these limitations from previous methodologies. So just to see here some examples, on the left, we see a deposit that with previous methodologies, it was found to be pretty small. And then when we look further, when we look with this methodology and we don't only trust the false color image, we see that it's actually much larger. Same for the Natia facula on the center. We see that in this case, our approximation with this cloud, in some areas, it matches the value found by Barrault et al. Where she was looking in the masks data. And then in other points, it's closer to values from Thomas. So it's actually more irregular than originally thought. And then in other cases, we see that the maximum extent of the maximum radius, let's say, of the deposit, it matches previous estimates, but then the area is actually smaller than previously reported just because the deposit is irregular. So these are things to take into account when then analyzing volatile content and other parameters. And finally, I will just show some deposits that were first documented by the IAU. And we see how the IAU sometimes shows some inconsistencies. And the good thing about this methodology is that it's using the same approach for all the deposits. So For example, here on the right, we see for the Orm facula how the IAU and our estimate are pretty close. But then, for example, in the left, we see that for the Hesiod area, some of the deposits found by the IAU are smaller than, and they are not connected, while we find that the deposits are actually overlapping and they are connecting. And we see the same behavior here with the Ago and Abeso deposits that are found as separate from the IAU. And then when we look both only from a spectral point of view and with this methodology, we see that they are connecting. And finally, just to show, this is my last slide, just to show some next steps on how this can be used as a first input to keep doing more research. What we want to do is now to use these limits of the deposits to be able to constrain the properties of the deposit related to the background. Since the deposits are mixed with the background terrain, it's important to have a good knowledge of where the deposit ends in order to characterize them. So this is part of the work that we want to proceed. And then another part is to study the age of the deposits. So since the deposits will be affected by different space weathering effects, they will actually become closer to the background terrain with time. So we want to test this theory looking at the properties of the deposits compared to the background terrain and comparing them to the degradation of the events themselves to be able to understand the relative age of different deposits. So for me, this is it. This is my summary slide, and now I will be happy to answer any questions that you might have. And thank you very much for your attention.